Hello, everyone. Thank you, Willem, for warming up the crowd. Fantastic first act. I'm Vincent Trussart, VP Software Architecture at Grass Valley, and Chairman of the Technical Steering Committee for the EBU DMF MXL initiative. This will slightly overlap with what you've described, but I'll take a different angle. So, over the last 20 years, 25 years in live production, we went from fixed function dedicated hardware solutions to completely dematerialized software-defined media functions that can execute on-prem, in container environment, or in virtual machines, or in the cloud, or even using accelerators in the cloud. The compute power, as you mentioned, is orders of magnitude what it used to be 20 years ago. I used to work on one of the first playout solution, one HD channel per full server. That's the most we could do with one box. Now we can do dozens of channels on a fat server. So it is massively more powerful. We have fast GPUs, fast network infrastructures. So we see that we have more available to us and more flexible execution environments as well. So if we focus on the second half of this, on the first half of the graph, what enabled this transition from fixed function to virtualized software is going from SDI to IP, for example, SMPTE 2110. Something that was great with 2110 is that it was kind of similar to SDI. Line alignment, pixel alignment, predictable timing. So all the attributes of 2110 of SDI were mostly preserved. It's the same mindset. So it's synchronous, it's real-time, it's clocked, which was comfortable for people who were used to SDI. Sorry, I lost one. However, if we look at the second half of the graph, where we go to purely software environments, these core attributes of SDI, of synchronicity, real-time, suddenly become a hindrance. If you want to execute multiple media functions back-to-back, you don't want to wait for the end of the frame to be transmitted to work on your next step, and you keep adding latencies. We also, for example, since COVID, everybody was cobbling together something based on NDI, CDI, SRT RIST, even within the same container environment, within the same server, looping in, looping out, again, adding latency. So there's something better that we need to implement. At Grass Valley, we've been building AMP for 7 years now. We've been using shared memory models, and this is something that we want to contribute and work with the DMF initiative to have a shared memory model. So Willem presented the layered approach for EBU DMF. MXL is focusing exclusively on the media exchange. This means that we're not covering provisioning on purpose. We're not covering flow discovery, flow registration. All of this is not part of DMF. So by itself, the DMF is incomplete. It will need upper layers to help you find, discover, register flows, but it's a fundamental layer that will enable us to build on top of. So yeah, exclusively focusing on MXL. Another analogy that we use at Grass Valley is MXL defines the plumbing, the utilities between multiple houses. Multiple vendors have their own platforms, software-defined platforms. We all have different platforms now. But we need a way to communicate. We need to be able to exchange the best-of-breed audio processing technology with the best-of-breed video processing technology. And customers want to have this flexibility. At the moment, it's very difficult to pick and choose software-defined media functions from multiple vendors in a single house or in the house that you get to choose. And this is what MXL will allow you to achieve. Quick timeline. As Willem said, last year, September, first discussion. In 2024, exactly today, exactly that specific day, the day before the end of IBC, I met with CBC guys, with EBU, and the idea was circulated, well, we should do something. So it's exactly 365 days today from this first day. And in this industry, we're not really great at moving fast, but within a year, we have pictures and interrupt, which I think is quite amazing. So it moved very, very, very rapidly. I won't go in details here, but Geneva, the Geneva Convention in November 2024. Multiple vendors, Tiger team. So yes, a Tiger team was formed, and as you said, rocks were thrown at us. But yeah, that's part of the design, the initial kickoff. But it was essential to bootstrap the initiative. By NAB this year, so there's a typo here, 2025, by NAB, we had our first internal demos. Pictures were moving, no sound, just video. It was about to get real, and it already raised quite a lot of interest from multiple vendors and customers. And people ask us, where's the code? It's supposed to be open source, but where's the code? Well, we could not release the code to a wider audience without a proper charter, a proper open source project. And this is what the Linux Foundation gave us, as you mentioned. It's a charter, it's rules of the road. So who's contributing what under which license? If there is a conflict, I want to do that and you want to do that, how do we resolve this conflict? So it actually took quite a while to get the charter in place, but once we had the charter in place, all the code was made available on GitHub. Everything is Apache v2 license, so no strings attached, but you need to release your code under the Apache v2 license as well. Everything is available on GitHub. Multiple vendors already active, showing demonstrations, showing live code, live demos, and interop already between vendors this year. So this is time to roll up our sleeves because it will be quite technical. So, hopefully this is what you came for. So after this Geneva meeting, we identified the key requirements. First one, we need to cover intra-host sharing. So I have multiple containers running on a big system. How do I exchange memory buffers? So that's what we call intra-host memory sharing. But it needs to also cover inter-host media sharing. So if I'm in a big data center, I have racks and racks of servers. They are usually connected using a very, very fast network environment, what we call a fabric. So on this fabric, this is nothing new for the IT technology. For broadcast world, this is something a bit new, or something that we never used. But RDMA, elastic fabric adapter, all of these technologies can accelerate media movement from one host to another without involving the software, without involving the operating system. So it's wire speed, as fast as it goes, as it can, it will saturate the link. So this is something that we should leverage. The IT industry, the AI industry is investing billions of dollars on this technology in all data centers. We should be using that. We should not try to invent something else and dispatch small packets every 7 microseconds, which is horrible. PCs are horrible at dealing with small packets, evenly spaced in time. PCs and servers are good at big buffers and bulk transfers. And this is what technologies such as libfabric, RDMA, and so on will provide us. And we're just building on top of the shoulders of giants. We're leveraging what the IT industry is doing and not building against it. We want optimal performance. For example, what I said about packetization across containers and then encoding SRT, this is a waste of resource. We're wasting a codec, we're wasting a decoder. Packetizing is expensive. Why are we doing that? The buffer is on the same machine. Share the buffer instead. So it's orders and orders of magnitude more efficient to just share a pointer or share a buffer than to encode and ship. So we're not doing that. So it needs to scale to thousands of flows, not just 10 flows, thousands, tens of thousands of flows on a single machine. And we want I wrote low latency. It's actually ultra low latency. If you have a line of a picture, if you have a couple samples, you can start consuming them as fast as possible. So we saw some graphs from one vendor comparing 2110 latency to be about 33 milliseconds for 1080i 59. RDMA was about 1 millisecond to move the full frame across the wire, and with the MXL it was 0. It's just instant, it's there. So fantastic latency, suitable for video use case and audio use cases. It's interesting, in the list of logos that you saw, you had video-centric vendors and audio-centric vendors, and their requirements are not quite the same. So the audio guys will want, I want every sample one by one, and the other guys, I will give you a frame, and that's it. So we have to accommodate the two use cases. Again, let's not reinvent what we don't need to reinvent. JTNM, Flows and grains model, it's well-defined, well-explained, well-documented, so let's build on top of that. And the NMOS JSON definition for the flows, it exists. It defines the width, the height, the bit packing, the resolution, and all that. Let's not invent yet another horrible way to describe video. There are many ways. Let's use what has been standardized. So we're leveraging what exists now, and we're leveraging terminology that we know. So for the broadcast industry, it won't be new. This is something that we know. This is a revolution. We're not working on a specification. We're not working on a document. We're working on an SDK. The measure of success of this project will be the delivery of version 1.0 of a production quality SDK that works across vendor, not a document. We've seen this with SRT versus RIST. SRT, SDK first, and we'll standardize it afterwards. Everybody got the SDK, and it just worked. And then RIST, write the spec, and then lots of different implementation that may not be compatible. So that's a good example why the SDK first is something that promotes interop, and that's what we're seeing today. After a year of development, we have interop. Small library. We want this to work on Raspberry Pis, embedded audio devices, to hyperscaler in the cloud. So must not bring Kubernetes with it. It must work with containers. It must work with Kubernetes, with cloud hyperscalers, but also small Raspberry Pis and small devices. We want this to be very scalable and work in multiple execution environments. Basically, it's no strings attached. We're not forcing the broadcast vendor to actually bring a full stack of software to get to MXL. It's a small library. As you said, security is super important, so we need to make sure that if I have two productions running on my server, vendor A or customer A cannot see the flows of customer B, so we have to protect, isolate, segregate the different flows. We also want to have a model where we can move and describe video buffers and audio buffers where it lives. So my buffer came on my GPU. I would like to leave it on the GPU until I need it on my host. My buffer is on my GPU. I need to send it to another GPU on another machine. I'd like to migrate the buffer to the other GPU without involving the CPU. So again, using fabric technologies to move the buffers elsewhere. Using acceleration if possible. Okay, I covered that. So how does it work? This is when we roll up our sleeves. Simple C API, C++20 implementation, modern code under the hood. The shim at the top is plain C for ABI binary compatibility over time. It's basically the flows and grains model. A flow has a unique ID like in NMOS. The flow for video and ancillary data, it's grains living in shared memory in memory. And each video frame lives in one grain. Simple. For audio, we didn't want to shoehorn the concept of audio into a video grain or something that is too big. So we have another ring buffer type. I think I covered that a bit later. Another ring buffer type, I'll cover that a bit later. So we want to memory map the buffers. So as a consumer, you just do an mmap of the memory region, and you have direct access to the buffer. You don't need to ask for the buffer to be sent or given to you. You read the buffer. We don't use the terminology senders and receivers. We use readers and writers. You read in place, you write in place. So again, more efficient. How does it work under the hood? By limiting ourselves to Linux or Unix-like environments, so no Windows support, by limiting to Linux environments or style, macOS works as well, we're using RAM virtual drives, RAM drives, TempFS, to host a region of shared memory. Why TempFS? Well, we need to find a way to share memory across containers in a secure manner. I don't want to give IPC access to all my containers running on AWS or running on my host. I want my IPC, my interprocess objects to be closed and secure within the container, but I want to put something in my container and make something available. In containers, you can actually map and mount a volume, a virtual disk. It's still just pages in RAM. It's not adding any very minimal overhead. But you can treat it as a virtual volume that you give to a container and you mount when you spin up your container, and then you can actually see the flows. Since It really just looks like a file on disk. You memory map that region, and you have access to the memory buffer. We want this to be super secure. So this is geek mode on, sorry, I just turned on the geek mode. We cannot even use a mutex or semaphore to access the memory region because you need write access in the memory region. We don't want to give write access to readers. So we're using a few texts under the hood so to detect when something has changed in the memory counter, and then the reader knows that something has changed without having to lock a mutex in that memory region. Geek mode off. So that's the end of the geeking out. But basically we want this to be super secure. Since it's a virtual file system, you get all the benefits of the Unix permission schemes as well. So I want my group called morning production, and my group called nighttime newscast. And you get groups and user and permission masks and bit masks to allow access or block access to some flows and give access to others. Since it's a virtual file system, you can even group your flows into virtual folders. We call them MXL domain. So I have my morning show. It's a domain where the flows live. I can have on the same machine, using the same compute, a second domain, a second volume that is actually customer X doing a game of soccer or whatnot. And then you partition your flows into different virtual paths. And then you map these domains into the containers. So the containers only sees what it needs to see. Again, very secure. It's very slow. Okay. Multiple types of ring buffer. I don't know how much time I have left. So the first one is the granular ring buffer for grains, like video, something that is fixed size, a video frame, something like a VANC packet, which has an upper boundary in 2110. So VANC and video, they go in a granular ring buffer. So a ring buffer, each slot index in the ring buffer is a different frame or grain. The time of the ring buffer is basically, you start with PTP time, the epoch. You divide by, you do a modulo of the duration of your grain, so 33 milliseconds or 20 milliseconds, and the remainder is the index where you should be. So it's basically continuously increasing index in a ring buffer. You know where the head is, the head keeps moving, and the readers can choose to read wherever they want in the ring buffer, which gives you lots of power. If you have cameras, for example, sending video from across the world, and you have another camera that's local, and if they carry their own timestamp, you can actually hide the latency because they actually can write at the right place in the ring buffer, and you can choose to roll back time and consume your flows synchronously between the two cameras. So one will have more data in the future, but you just read a little back, and then you can realign perfectly the two flows because you have enough history in your ring buffer. The history, the size of the ring buffer is configurable per domain. So there's an option file where you can increase and make the history bigger depending on your use case. Again, here, so the grain rate is the frame rate. So that's super simple. It's super low latency because when you read a grain, so the API is MXL get data or get grain. I can't remember what the API is. You get the data with a timeout. If you get something, you have to look in the header. You know what? This is a grain. It has 20 valid bytes out of 5 megabytes. So someone wrote a bit of data in it, and it is incomplete. So the reader must verify if the data is complete, allowing writers to write line by line if they choose to do so. So if you have a JPEG XS decoder that can decode a couple lines, you can actually write them as you go and be very low latency. So that's what we call slices or partial grain. It doesn't really need to be a slice. It's not 8 versus 4 versus 16. It's some data is written, and you have to verify if it is complete. I said multiple readers, but you can also have multiple writers in the same ring buffer. So if you have redundant flows, and if you can guarantee that you have -7-like reception, so the perfectly identical data coming on two paths, could actually have collaboration between two writers. So if one goes down, the other one carries on, and you have redundancy at the flow writing time, and multiple readers, not just two, as many as you want, readers that can choose to read now or slightly in the past and so on. For video, we chose to limit as much as possible the video formats that we want to support to promote interrupt, and that's the reason why we had interrupt. So the Zoom guys will want RGB 445, RGB 888, and some guys will want planar 16. And we had to choose. We had to choose something that is suitable for most use cases. Broadcast is still 10-bit YUV422. So the V210 format, packed format, lets you carry 10-bit YUV422, SDR or HDR. So that was good enough for 99% of what broadcast is, so we settled with that. Ancillary data, it's the RFC 8331, which is the RFC used by 2110-40. So it's exactly the same without the RTP header at the top. How much time do I have?
It's good.
Okay. So I said it's a virtual file system. So this is what it looks like. So look at the recording if you cannot see what's written. But basically, this is the flow ID .mxl flow. That's a folder. That's a directory. And within that folder, you have the data header, the grains subfolder. So this is the header where you have the few text that will tell you something has changed. So you listen for updates in the data object, the flow info object. Then the grain subfolder has as many grains as it needs for the history duration that you chose in your options file. So this subfolder has 5 HD pictures of type V210. And as a reader, the SDK will let you memory map these regions and consume the buffers without any single mem copy. The .json here is really just the NMOS JSON flow definition as found through the standard schemas in NMOS ISO 4. Any questions about that?
Yeah, you're about one.
Okay. Audio, mostly the same, but since audio is high frequency and it doesn't have the notion of grain, we're storing planar audio, which is weird. It's basically one big buffer, and then you have first channel, second channel, third channel, so it's multi-channel audio, if you choose to have multi-channel audio. All the samples are ordered per channel, making it easy for you to derive a pointer and just iterate over the samples. You don't have to demux or anything like that. Structured slightly differently. I won't go into that. Important, we're leveraging libfabric to move grains and move buffers around from sources to destination. This is something that is still being worked on, not available at the moment, will be available as part of version 1.0. So roadmap to version 1.0. We need to add audio-video synchronization objects. So it's easy to consume audio, it's easy to consume video, but if you want to consume from both ring buffers, how do you synchronize everything? So we'll add that. Fabrics API, as I said, a Rust API and GStreamer native plugins written in Rust that will let you do full I/O using GStreamer. You need to define a qualification and validation process. We want when 1.0 is released, we want broadcasters to be confident this is compatible, it will work with everywhere. So we want some kind of approval or qualification process, documentation, bug fixes. Post 1.1, another type of ring buffer that will allow us to carry data that is timed, not periodic, and random size. So it doesn't fit in any ring buffer, but if you think about 2110-41 or fast metadata FMX, we need to be able to carry something like that to carry audio metadata and so on. So this is coming soon because we know we need that. What's next? It's going to be defined by the requirements console. So we're not inventing stuff. It needs to go through the requirements console, and then the technical steering committee will start implementing the features.